Hello, class. This is Mr. Hart. And in this podcast, we want to talk about the second part of special relativity, and that's dealing with the phenomenon of length contraction. Okay? And to kind of understand where length contraction comes from, I want to tell you a little story about a particle called a muon. Okay? Now, this is just a artist representation, but it looks pretty cool. But muons are these particles that kind of come from the upper atmosphere. They're generated when solar flares occur and other things happen in the upper atmosphere. And they're just very short-lived particles. Okay, if you look at the lifetime of a muon, its total lifetime is 2.20 microseconds. Okay, or 2 millionths of a second. Okay, so they're not around for very long. They kind of are generated and then they disappear. Okay. And we can detect these muons on the surface of the Earth when these solar flares come and things happen. But that's weird because if the muon only has that short of a lifetime, okay, scientists started realizing, hey, if we're picking it up on a detector on the ground and it's supposed to travel all this distance from the upper atmosphere down to our detector, okay, even if it's going ridiculously fast, zero point 0.9 times the speed of light or something like that, it shouldn't be able to cover that distance. It should die before it ever reaches one of our detectors. You take that time, times it by the 0.9c, it should only make it to, this distance in the atmosphere, right? It should die before it reaches us. So scientists were kind of confused when they first saw this, because based on the short lifetime and how fast they were going, it shouldn't be able to make it. But what they realized is that special relativity was starting to come into play, okay? Now, you could think about it in terms of time dilation, but they also realized that length itself kind of appears to be contracting. It appears to be shorter to things that are moving faster. Okay, so you don't have to consider both factors. You don't have to consider time dilation and length contraction at the same time, but it helps to think about certain problems in terms of length rather than time. Okay, you think of the length as shortening rather than the time speeding up or slowing down. Okay, and so on your homework, this is actually one of the problems. You get to figure out how fast the muon's going, or basically how much length contraction is occurring to make it reach the detector. Okay, in college they say that's a problem left to the reader, which just is a mean way of saying, yeah, you're gonna have to do this yourself. But anyways, the point is you'll get to look at this problem. But basically what length contraction is just a rewriting of the time dilation equation in terms of distance rather than time. So now in this case, you'll notice it's very similar to the time dilation equation, except now it's just distances or lengths. So this is the length to an observer. Okay. This is the length perceived to the person that doesn't think they're moving in their reference frame. Okay. Again, I don't know how to write that succinctly. Okay. But person doesn't think they're moving, sees this length. Okay. And then gamma is, again, the Lorentz factor. Okay. So notice the Lorentz factor is the exact same. It's still described the same way mathematically, but now its description is a little bit different. It's a ratio still, but now it's describing how much shorter a distance is compared to another distance, right? You're dividing by gamma now. So it's saying this length is going to appear this much shorter to someone moving faster. Okay. And that's how it works. Okay. Again, don't worry too much about which length is which. As we go through the problems, it kind of becomes clear what you're dealing with. In other words, this length should always appear shorter than that length. Okay. So let's go ahead and just look at an example problem. Okay. So a 2.3 meter long sedan is traveling at 0.876 times the speed of light. What is the perceived length from an outside observer? Okay. So in this case, we know that the length from the reference frame is 2.3 meters. And we know that v is 0.876 times the speed of light. And now we want to figure out, what it looks like to an outside observer. So just like before with time dilation, first let's find out what the Lorentz factor is going to be. Okay. So gamma equals 1 over square root of 1 minus v squared over c squared. Okay, we'll plug in v squared. So we get 1 over square root of 1 minus 0.876 squared, c squared over c squared. Again, c's cancel out, which leaves us with 1 over square root of 1 minus 0.876 squared. Okay, so we can plug that into our calculator. 1 divided by square root of 1 minus 0.876 squared. And we get that gamma, in this case, or the Lorentz factor, is about 2.07. Okay, or in other words, time slows down by this much, or I guess flows faster for the observer by this much, or the distance or the length is contracting by this much. Okay, so now if we go to our problem, we say, okay, we know that L equals L naught over gamma. So L in this case equals 2.3 over 2.07. Okay, and when you divide that on your calculator, you get that the perceived length of that sedan is 1.11 meters long. Okay, so that's about 4 feet. Okay, so that 8 feet car just turned into a 4-foot car. Okay, if you're observing it. Now you probably wouldn't see it for very long because it's traveling almost the speed of light, but if you could see it, you'd see that it's much shorter to your vision than it is usually. Okay, so it's 1.11 meters long in that reference frame, or from that observer's frame. Okay, all right, let's try another one. Okay, so a student driver accidentally runs a red light and their back car tires are on the white line. However, they hope that they will not get a ticket because of length contraction of their car. By the way, don't ever depend on that. If their car is 3 meters long and the white line was 2 meters back, how fast must they be going to not get a red light ticket? Okay, so just like in a problem in the previous podcast, let's just think about what the Lorentz factor would be. Okay, if we want to be 2 meters back when we were actually 3 meters back in our reference frame, okay, then we need to be 2/3 as long, right? Or in other words, gamma needs to be 3 over 2, okay? Again, gamma is always going to be larger than 1, okay? And because we're dividing the regular equation, we want to be 2/3 the length. We need gamma to be 3/2. Okay, that's the ratio we're looking for. Okay, so now we just solve this equation. Gamma equals 1 over square root 1 minus v squared over c squared. And again, we just solve that for v so we can figure it out. And in the previous video, we did this derivation. We showed that v over c equals the square root of 1 minus 1 over gamma squared. Okay. Now again, I left c on there because we want to think of our answer in terms of c. Okay. And now we can just plug it in. So we get square root of 1 minus 1 over 3/2 squared. Okay. So at this point, I'm just going to plug it into my calculator. And when you plug that all in, and when all is said and done, you get that v over c is 0.745, or in other words, v equals 0.745 times the speed of light. Okay? So, unless you were traveling at 0.745 times the speed of light, that student driver does still get the red light ticket, and they probably would still get a speeding ticket if they were going that fast anyways. All right, anyways, let's move on. Okay, so that's how to do problems with length contraction. Again, if you do length contraction, you don't have to do time dilation. They're just different manifestations of the same effect. But certain problems are easier to think in terms of length, and some are easier to think in terms of time. Okay. All right, let's talk about one more thing with special relativity, though, to kind of think about, and that's what we call simultaneity. It's kind of a cool word. It just basically means that we think of things as happening at the same time, simultaneously, right? So generally speaking, we are moving so slow that we consider time to flow at the same rate for everyone, right? When you run past your friend in the school, you don't see, your time slow down for you compared to him, okay? This means it's easy for us to say that two events happened at the same time, okay? We both, clapped our hands at the same time. We both jumped in the air at the same time. That's easy to determine at our slow speeds, okay? But when it comes to relativity, that really becomes a problem, okay, when we get to higher speeds, okay? So you and I jumped at the same time only makes sense when we share the same reference frame. If we get to higher speeds, that's not the case, okay? So when we get to relativistic speeds or super fast speeds close to the speed of light, simultaneity is no longer commonality, okay? You cannot say that something happened simultaneously in your reference frame and assume that your friend had it happen at the same time in his reference frame, okay? For example, if you had someone in a train, moving past you close to the speed of light, okay, and two people, one on the train, one off the train, clap their hands, okay, you might see them as happening simultaneously, whereas the person on the train won't see that and the person on the ground won't see that. Okay, we run into these issues because time is flowing at different rates for us, okay? So, for example, a person standing still may see two events happen at the same time, but they do not occur at the same time in a moving reference frame, okay? So with all of that being said, the main point is to realize this means that simultaneity is not consistent between relativistic frames, okay? We can no longer say that events happen at the same time in special relativity, okay? It just doesn't make sense. They can happen at the same time in one reference frame, but they won't in a different reference frame, okay? So simultaneous events no longer apply, okay? There's a great video, a great animation that kind of shows this. It's at this link, and I've posted it to the website. Please make sure you watch it. It just really describes well and shows well how events don't occur simultaneously at these speeds, okay? But that's it for this lesson. Make sure you do the homework on length contraction. Let me know if you have any questions, and thank you for watching.